Alright, welcome back. So in this particular video, we're going to consider what is called the support vector machines. So in the previous videos, we've seen several different machine learning algorithms, such as the linear regression, the logistic regression, the k-nearest neighbor, the naive Bayes. So we've actually considered all of these machine learning algorithms, and in this particular video, we're actually going to consider what is called the support vector machines, right? So this support vector machine can actually be used for both classification or regression problems. Mostly we will be seeing this used in classification problems, but we can also use it for classification problems, right? Mostly we will use it for classification problems, but we can use it for regression problems as well. All right, so we will first go to our whiteboard, then we get an intuition behind what is meant by support vector machines. Then we move on to the lab session, where we will do practical implementation of the support vector machine and the concept that we will learn when we go to the whiteboard. All right, so without much ado, let's head on to the whiteboard and then let's start getting an understanding of what support vector machine is all about. All right. Okay, so over here, what we're going to do is to try and then make everything more intuitive, right? So let's take an example. I mean, I like giving an example because I realize that actually gives more understanding as compared to just me speaking to you and you just imagining stuff. So let's start by first doing something here which will make us understand. So okay, so let's take this one as our x and then y-axis, right? So I'm going to just plot some points here. So let's say we have some blue points and then some black points, right? So let's say we have some blue points over here, right? So let me just put some blue points over here. Okay, so let's say these are our blue points, and then let's say we have another set of another group of points over here, right? So we have another group of points also here. Okay, so now these are the two groups that we have, right? Now we can see that these two groups are linearly separable, right? They are linearly separable. Right, they are linearly separable, right? Because we can actually draw a linear line over here, right, to separate these two groups. Then I can just maybe call this group A and then group B, right? I can easily draw a linear line to separate these. So I can say that they are linearly separable. All right, now if you look at this carefully, I can also draw a line. I can also draw the line this way, right? Maybe this is not a good line. Let me draw a different one, right? I can actually draw a line this way to also separate it, right? Or maybe I can draw a line this way to separate it, right? So you can actually imagine how many different lines that I can actually draw to separate these two groups, right? So I can draw several linear lines to actually separate these groups. So that's some of the problems that we might face, some of the challenges that we might face if we want to separate groups like this, right? If we want to draw a linear line to actually separate this. All right, so finding the best line, line, all right, separable line to separate these two groups is what support vector machine is all about, right? That's what support vector machine is all about. That is helping us to actually find the best line, right? So in this case, it's just in two-dimensional space, right? It's just in two-dimensional space. So if we have it in more than two-dimensional space, then maybe for example, say three-dimensional space, then we can call this. So in this situation, since it's in two-dimensional space, we're calling it a line. But if it's more than that, we can call it a plane, right? A plane, right? And then or maybe a hyperplane, right? A hyperplane. Okay, we can call it a hyperplane. Okay, so finding the best line or finding the best plane or hyperplane to separate these two groups is what support vector machine is all about, right? That is what support vector machine is all about. Now let's see how support vector machine will actually find the best line over here, right? Let's see how support vector machine will actually find the best line over here. Okay, so I'm going to draw this. Let me just draw this one again over here, right? Let me just draw this. Okay. And then let me draw, let me put on our points, right? So we're having these points. So having our blue points over here. So let me just quickly put these blue points over here. Okay, then we're having our black points somewhere here. All right. So these are our two groups that we're having. All right. Now, what support vector machine will do is that it will try to draw a line, right? So let's say we have this line. Let me draw a line here to separate these two. So let's say this is one line that separates the two. And then let's say this is another line. Let me actually change the color. And then let's say this is another line that separates the two. Now, what support vector machine does is actually to calculate the margin, right? The margin is nothing but how far can you move parallelly before you encounter the first blue point, right? So for instance, if you pick, let me actually call this line A, right? So let me call this A, and then let me call this one B. Okay, so if you pick say line A, how far can you move before you hit the first the first blue point, and then how far can you move before you hit the first black point, right? If you hit the first black point. Okay, so that's what support vector machine will do. That's how it will calculate the margin. So what it's actually going to find is what is called the margin, right? It's what is called the margin. Okay, it's going to find the margin. So it will actually calculate, let's say this, right? This is the first blue point, right? So this is it. And then it will also check for the first black point. So let's say the first black point is this one, right? So something like that. Right, so we hit the first black point over there. Then it'll check the distance, right? This is the margin, right? For that is the margin for A. Then it will do the same thing for the B line also, right? So let me actually change this to say green, right? So how far would it go before you hit the first green, right? Like that. And then the first black. So let's say this is the first black, right? So how far would it hit that? Okay, so this becomes the margin. This becomes the margin. Okay. So in this case, what is actually going to do is that it's actually going to see which one is having the higher margin or the highest margin in this particular case, right? So it's actually going to draw different lines. I mean, it's going to be several lines, not just only these two lines, right? Not just only line A and line B, but we're going to have several lines that support a vector machine will actually draw to separate these two groups, right? And then calculate the margin for each of the lines, and then find the line that is having the highest margin. All right, so in this case maybe we can say the line B is having the highest margin, right? If it calculates and the line B, maybe the distance here is say 12, and then the distance here is say maybe 11, right? Then it will say that okay, line B is the best hyperplane, all right, or the best plane or hyperplane, right? That's the line that separates the two groups of the best, right? So it's actually going to choose line B, right? If that is the one having the largest margin, right? So basically what we look for is the higher margin, right? The line with the higher margin. That's what support vector machine will actually do. All right, so the support vectors are these points, right? That are closest, the points that are closest to the line, right? So in this case, if we choose B, right, then the points that are closest to B, right, the points that are very close to the B line is what we refer to as the support vectors, right? Those are the support vectors, right? That's why I refer to it as support vector machine. So the points that are closer to the best line, right, or the best hyperplane is what we refer to as the support vectors, right? So this is a support vector here. Right, this is a support vector here, right? There's another support vector here. So those points that are closer to the best hyperplane is what we refer to as the support vector. Okay, that's what we refer to as the support vector. So in summary, what support vector machine does is try to find the best line that separates the two groups, right? Try to find the best line that separates the two groups. Now, and as I said, if you have it in just two-dimensional space, then you can just call this best line that separates the two groups. You can just call it a line, right? But if you have it in, say, that is a line, and then with the equation as y equals, you can have, say, a plus bx, right? Something like that, and then if you have it, you can have a situation where you have it like y equals, you have several x, right? Instead of just having just a single x, right? You have several x. So in that case, it will not be in just two-dimensional space. It could be in, say, three-dimensional space, right? So you can have another line here. Maybe this one will be x2, right? So this one will be x1, something like that. So you can have a plus bx1. And then you can have h2, right? So b2, right? Something like that. In this case, you can call it a plane, right? You can call that line that separates the two groups, you can call it as a plane, right? And if you have more than that, maybe you have y equals, say, a plus bx1 plus say b2x2 plus, say, b3x, oh no, bx then x3, right? Something like that. You can have it, you can have it, a lot of them, right? In this case, you call it a hyperplane, right? We call it a hyperplane. Okay, so this is basically that is it. It's just the same thing, but depending on the dimensions, right? So if you have it more than two spaces, right? Not in two-dimensional space, in just two-dimensional spaces, you can just call it a line, right? More than that, you can call it a plane, right? And if you have it in more than three-dimensional space, you can call it a hyperplane, right? So basically that is the name that we give to this line that separates the two groups. Okay, now this is a situation where we have two groups that we can just draw a line, right, to separate these two groups, right? You can just draw a line to separate these two groups, right? And then you can see that these two groups are just clearly separated with the line that we draw in between them. All right, now there could be a situation, where you cannot just draw a line to separate the two, right? Let's see an example of that, right? So in this case, we say that it is linearly separable, right? It is linearly separable because we can draw a line to separate these two groups, right? We also have a situation where you cannot actually just draw a line to separate these two groups. So let's say I have let me draw these lines again, right? So let's say I have this. Okay, so this is what let's say I have this one. Now, if I have the points like that, so I have my blue points over here. Okay, so let's say I have my blue points over here. Then I have let's say I have some points, some other points, maybe. So let's say I have these red points also over here. So earlier on, we were having it something like this, where we can just draw a line to actually separate these two groups, right? Now, let's consider a situation where it's not just like this, but some of the red points have crossed over to this part, and then you see that some of the blue points, right, some of the blue points have also crossed over to this point, right? Some of the blue points have also crossed over to this part. So in this case, it's actually going to be difficult to just draw a line, right? So if in this case, if I just say that, okay, I'm going to draw a line over here, right? If I say that, okay, I draw a line over here to separate the two, right? Now you can see that I have some red points over here, and I have some red points over here. I have some blue points over here, right? You can even see some blue points over here, right? In this case, I'm not able to perfectly separate these groups, right? It doesn't matter how I draw this line, right? Even if I draw it like this, right, still now I am not able to separate it. If I draw it like that, I'm not still able to separate it. Okay, so in this case, we have lines that are crossing over here, right? We have we have points that are crossing over here, right? In this case, we have some blue points that are crossing over here. Now in this case, if I want to draw the margin, maybe the margin will go this way, right? Of this margin, and then something like this. Then it will touch the first support vector over there. Okay, so maybe I have it like that. Okay, so this becomes the margin, right? I have the margin over here, and then I have my plane over here, or my line, which is actually separating these two groups, right? Which, I mean, not perfectly separating them, right? But we have well, let's say this is the best line that we can find over here. Now if we do that, we can actually see that there are some points that are crossing over, right? You can see that there are some red points, right? Some red points that are actually crossing over, right? We have some red points that are actually crossing over here. Similarly, we can see that there are some blue points that are also crossing over here. Okay, so what support vector machine is going to do in this particular case is that it will still go ahead and then separate these two groups, right? They're still going to go ahead and then find the best plane to actually separate these groups. Now what it's going to do is that each time a point crosses over, right? Each time a point crosses over to the other side, whether to this side or a point crosses over to that side, right? Each time a point crosses over, it's going to actually calculate what is called a penalty, right? It's going to calculate a penalty. Okay, now remember that over here, all we're trying to do is to find the plane, right? All we're trying to do is to find the plane or the line, right? So in this case, we say that B was the one that was, that was the best line. So what we're trying to find is that we try to find the line with the largest margin. So we try to maximize, right? We try to maximize the margin. Okay, we're trying to maximize the margin, right? That's basically what we're doing over here. It's the same thing over here. We are going to find several lines or planes over here and then choose the best one, right? So in this case, let's say that this one is the best, that is working for us, right? So this is the largest margin over here. So in this case too, the same thing, we maximize the margin over here, right? We maximize the margin over here. Now you can think of maximizing the margin, right, as the same thing as minimizing 1 over the margin, right? You can also think of it this way. Now remember, if we are considering the fact that we want to maximize the margin, then we can say that, okay, a line with a margin of say 25, right? A line with a margin of 25 is better than a line with a margin of say 15, right? And it's better, a line with a margin of 15 is also better than a line with a margin of say 5, right? So we can actually do that. All right, now this is the same thing as if you take the inverse of them, right? If we take the inverse of them, for instance, if we take 1 over 5, right? 1 over 5 is actually going to give you something like 0.5, right? And then see, if you take say 1 over 15, right? 1 over 15 is actually going to give you something like 0.06, right? And if we take say 1 over say 25, 1 over 25 is going to give you 0.04. okay, Right, now you can see that as the margin increases, that's the denominator over here, right? So this one is actually the inverse of it. We are taking 1 over the margin. So if the margin is, say, the margin is 25, we like that one which is greater than, say, 15. And if they say 15, we know that that one is better than the one with in the margin of 5. Okay, so in this case, if we take the inverse of it, then this one becomes better than that, right? And this becomes better than this one. Okay, so instead of maximizing this, instead of just saying that we want to maximize the margin, that is finding the line with the largest margin, we can also say that we want to actually minimize, right? We want to minimize 1 over the margin, right? We want to minimize that because as the margin increases, right? As the margin increases, that's the denominator over here. As it increases, then this becomes smaller, right? But we don't want small margins, right? We want large margins. That's why we want to minimize it. Okay, so we want to minimize the ones. We want to minimize the ones that are having the highest denominator over here. That is going to give us small margins. We don't want that, right? We try as much as possible to minimize that. Okay, we try as much as possible to minimize that. That's why we want to minimize that. Instead, I'm using this because I'm going to actually add something to this, right? Instead of just maximizing this margin, I'm going to add something to this one. All right, so now in the case of non-linear separation, so in this case we have a non-linear, right? These are non-linearly let me do it. In that case, this is a non-linearly separable, right? Unlike this one that is linearly separable, where we can just draw a linear line and then separate the two groups, right? You can just draw a linear line and then separate the two groups. In this case, we cannot just do that, right? There will be crossovers, right? So this becomes a non-linear separation. They become non-linearly separable, right? This becomes non-linearly separable. All right, so in that case, what happens is that we add a penalty, as I said, and each time a point crosses over, right? Each time a point crosses over, we add what is called a penalty. So instead of just this equation, instead of just minimizing 1 over the margin, right? We minimize 1 over the margin, all right, but we add a penalty, right? So some lambda, right? Let me even do it this way. Some lambda penalty, right? We add some lambda penalty to it. Okay, so basically that is it. We just add some lambda penalty to just this one that is just minimizing. So this is a case where we have a linear separation, and if we don't have a linear separation, then we just add a penalty. That is each time a point crosses over, right? And the common penalty that people actually normally use is what is referred to as the hinge, right? What is referred to as the hinge loss. Right, that's the common penalty that people normally use, right? So that's basically what you can actually see over there, right? So this is one of the common penalty that people use. That is a hinge loss. So what to actually do is that if there's a point that has crossover, right? For instance, we have this point here which has crossover, then we will calculate the distance between the points, right? The distance between the point and then the margin, right? So in this case, maybe we got 15, right? So this becomes the penalty, right? For instance, this is also another point over here. There's another point that has crossover, blue point that has crossover. So we're going to calculate the distance from that blue point and then the margin, right? And then maybe here is going to be, say, 2. So this becomes a penalty, right? So that becomes the penalty that we're going to add over here. That becomes the penalty that we're going to add over here. So if there's a crossover, then if there's a crossover, right? If there's a crossover, crossover point, then hinge loss, right? Hinge loss actually becomes the distance, right? Becomes the distance from that point to the margin, right? From that point to the margin. Okay, and if there are no crossover, if there are no crossover points, then the hinge loss will be 0, right? The hinge loss will be 0. All right, if there are no crossover, then the hinge loss over here is going to be 0. But if there are any if there are any crossovers, then this penalty is going to be the distance from that point, right? The distance from that point to the margin. Okay, the distance from that point to the margin. All right, so this is a two situation that we have seen where we have a case where we can just draw a linear line to separate the two. That is a linearly separable situation. And then we also have another situation which is non-linearly separable, where each time we try to find the best line to separate, or the best plane or hyperplane to separate the groups, we actually get to realize that there are some crossovers, right? There are some crossovers, and what we do is that we still go ahead and then find the best plane or the best line, and after we do that, each time a point crossover, we add a penalty to our function that we have over here, right? So we just add a penalty over here, right? So, and the common penalty that people use mostly is what is referred to as the hinge loss. And if we have a crossover, then the hinge loss is actually going to give you the distance from that point to the margin, and if there are no crossovers, then our hinge loss will be 0. Okay.